Hello
Good.
and welcome and cheers to whatever you're drinking today, whether it's a beer or a coffee, whichever time zone you're in. And welcome to actually one of in fact, our most RSVP session on the virtual jug today. That was previously James Gosling, and now today it's Alexei Shiplev. Alexei, how are you doing? And welcome to the VJug. How's things? You're on mute, Alexei.
Yeah, I think this auto detection thing actually thinks that I'm typing something when I'm speaking. All right. I'm good. I'm ready for this talk. I hope you're ready as well. It would be a long talk, so brace yourselves.
Well, absolutely. And yeah, apologies for that. Google Plus thinks that Russians sound like keyboards, so sorry about that. Oleg, welcome.
Hi, guys.
How's things?
Oh, I'm very excited about the session. I've seen a couple of short videos, excerpts from this when Alexei gave that on some Russian local jug meetings, and I'm super pumped to see this in full.
Awesome. Well, I've just started screen sharing, so I'm going to just show you what we've got coming up today. So this is it, the Java memory model pragmatics. Java memory model, something that is kind of fundamental to really all Java developers. Absolutely something which should be understood clearly, and that's why we've got local resident oracle, as it were, Alexei Shiplev, who also works for Oracle. Just a quick mention about our sponsor for the VJug. We have Zero Turnaround, a creator of revolutionary developer tools. I've talked about JReble and XReble before. Today I'm actually going to give you a very, very brief demo about a new tool which was released about 30 minutes ago called Optimizer for Eclipse. And let me give you a very, very quick demo of what that does. So here I have my Eclipse environment. This is an Eclipse IDE. I've literally done a search in the marketplace for Optimizer. Here we have the Optimizer for Eclipse version 1. This is just a very, very small plugin. I'm going to install this, and what this plugin is going to do is it's going to examine my Eclipse IDE. Let me just install that. It's going to examine my Eclipse IDE and try and find potential configuration issues in that Eclipse IDE. It's going to try and provide recommendations as to how those configuration errors can be resolved. So I've installed my Eclipse plugin, the Optimizer for Eclipse plugin. This is a free plugin, by the way, so it's available for everyone for free to speed up their Eclipse environment. I start my Eclipse for the first time with that Optimizer plugin installed, and obviously, this is a fresh install of Eclipse. Obviously, the longer you go with Eclipse, it's potentially going to get slower and slower with the number of plugins and the number of plugins and the number of history in your workspace and so forth. And this Optimizer for Eclipse screen will pop up, and here we can see we can do a number of things, such as tuning memory settings, disabling class verification. If your indexes and history have been around for too long, this can cause huge delays. Making sure you're on the latest version of the Oracle JDK and also the latest Eclipse version. And also, if you're interested in skipping your builds and redeploys, or skipping your app server restarts or Java restarts, you can also install JReble here. So I can just run a couple of changes. I can implement those recommendations very, very quickly. Click restart Eclipse, and this will provide me with those updates directly into my Eclipse for me. I don't need to do that manually. And now the second time that this runs, what this is effectively going to do is it's going to retime my Eclipse environment. And when we see the Optimizer pop up again, okay, this time we didn't save time, but normally this will provide potentially huge savings. And this is the vanilla Eclipse. I haven't actually done much development in this Eclipse yet. So yeah, give that a go. You can have a look at that now. Optimizerforeclipse.com, and if you're struggling with a slow Eclipse, then that could be very, very valuable to you. Okay, so without further ado, I'm going to hand over to our main man, Alexei. And Alexei, you're going to talk us through everything we need to know about the Java memory model.
Oh, yeah. First, a word of warning that I was thinking that I'm understanding the memory model for, I think 17 times in my life. And this is my 18th time that I think I understand memory models. So listen to what I will be saying with and take it with a grain of salt, because that's how this things works. I will try to do this to decipher this spec at the best of my ability, but I could be mistaken. Do not. Well, if you are quoting me on something, first try to understand it yourself and see whether I'm wrong or I'm correct. All right, so let me switch to my slides. Okay. Can you see it?
Yep, I see that.
All right. So Java memory model and the pragmatics of it. Let's see. So first, I have to show you this slide, which basically says, well, whatever I will be saying, it's not the something that you should base your commercial decisions on. And this is very handy for me because I can tell you lots of things and not be responsible for that. So this is the safe harbor slide for us. Right. Going to the intro, when I built this set of slides a year ago, I actually understood that my understanding of memory model is subpar, and so I tweeted this, that I have my relationship status is complicated with Java memory model, and Gustav replied that, well, no wonder, because the relationship should be built with bridges, not fences. All right. Let's first define what is a memory model. Let's set some expectations of what we will be talking about this time. So if you read just about any language spec, you will see that there are two parts in that spec. First part describes the syntax of the language, meaning how can you describe the particular things in the language with the text. And the other significant part of the spec is the semantics of the language, which says, what does those particular construction mean in the language? So most of the programming languages specs are implicitly or explicitly defining the abstract machine that executes the program in this language. And in that regard, the language spec is just the abstract machine spec. The very trivial example is if you know the esoteric language brainfuck, which is really, well, it lives up to its name, then you will realize that you are looking actually at the assembly language for the Turing machine. And the description of the brainfuck is literally the description of the Turing machine. So when you are describing the language spec, that means you're describing abstract machine spec. And if your abstract machine has state or has memory, the significant part of that specification is the model of how machine storage operates, and that is the memory model. It turns out that in order to serve the purpose of memory model, the memory model should only answer one simple question. And that simple question is, what values can a particular read in the program return? Well, or what value will particular read in the program read from the memory? It turns out that it is a very simple question, but the answer to that question is really, really complicated, and that's the very core of the memory model. So when you are dealing with sequential programs, when program executes sequentially, the memory model is really, really, really obvious. If you have the single-threaded program, then the reads that you execute in the program should see the values written by the latest write to that particular location in the program order. Which means that if you have the some write in the program, you should see it after in the next statements. And people actually not, for the sequential programs, they don't use Stern memory model. they usually means that the memory model is the part of the spec which covers the semantics of the multi-threaded programs. But even in the sequential programs, it's not really that easy. There is the famous C example, which is on this slide. When you have the local variable I, and you have the initial value 5 there, and then you have the feared construction there, which says plus plus I plus 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 I, and then you want to assert whether I, after executing that statement, is 13. So if you read the actual spec for C, you will see the notion of sequence point there. And the sequence point in C is something that is a particular point in the program where all the effects from the preceding statements have their effect, and no other statement after the sequence point has effect yet. So if you have multiple operations between sequence point, like we have here, we have two pre-increments and the addition between two sequence points. This is the undefined behavior. Spec actually does not tell you what would be the result of I. It could be anything, and that assert could actually fail. Now you can argue that this example is about the evaluation order, because it would seem naively that the answer really depends in which order the compiler will emit the operations there. But spec does not concern itself with it. It says that any value is possible here. This is the undefined behavior. So memory models, in the memory model sense, if we want to reason about what's the value of I here, we can actually reason about what would a particular pre-increment of I read from the memory, and what it will write there. So memory models sometimes also needed to reason about the single-threaded programs. So this is the really short academic intro. If we come back to the reality, if you have this big book of the language spec, then the language implementations are ought to do either of two things. Either they just emulate the abstract machine which is defined by spec, and run this and feed the source program to that emulator, and thus execute the original program. This way we can say that we are interpreting the original program, and this process is called interpretation. Or you can actually look at the source program and generate the specific machine code for the every statement and every action in the program. Cram it up in the large binary blob and execute the binary blob on the target machine, and we call this process compilation. Why do I have this slide? To remind you that in both cases, the implementations should match the semantics of the abstract machine. The people will tell you that the memory model is something that prevents compilers from wrecking your code, but it's not only about compilers. If you have the bug in the interpreter, which violates memory model, it could break your code. The simplest example, if you just cache the field values that you read before in the method in some internal interpreter table, and you're done for. This is probably not Java memory model compliant. All right. So the memory model in this parlance is the trade-off. It is a trade-off between three things: how hard it is to use a language, meaning how hard it is to write the programs that you can reason about; how hard it is to build the language implementation, and how hard it is to build the appropriate hardware. You can, if you're the language designer, you can request a particular sweet feature, like, if you're calling method system dot bring me my slippers, and you define it as, if I call this method, that JVM should bring me my slippers. You can put it in the spec, but you will waste considerable time building the conforming implementation for it. So there is some fine line between what we could specify in the language and what can the implementation provide. And since the language implementation works on the particular hardware, we should also look there. So the logic of this talk, given that trade-offs, is as follows. We would like first to express our desires for the language semantics, what we would like to see in the language. Then we will look what is actually available in the real world. Then we understand how the spec tries to balance between these requirements of what programmers want and what we can actually pull off. And sometimes we will see how the conservative implementations work, and maybe peek at some other languages. So we will have a few formal JMM definitions. I will try to put it in the blocks like here, like this. All right. We have 5 large sections. We will take a short break after a few of these sections. Let's start from the simple one, access atomicity. First, a note about the formalisms. I would use these examples like here below, and you should read it as follows. What's there in the columns is actually the code that executes in the distinct thread. So T equals V2 is something that is executed in the first thread. And the R1 equals T and the cert is something that executes in the other thread. And the actions that you execute in the first and second threads are concurrent. What you have above is something that had happened before any of the threads had started. So it's some setup there. So in this formalism, as access atomicity means that if you have any built-in type T, and if you have initialized it with the value v1, and we write value v2 in one of the threads, and we read it back in another thread, we can only read v1 or v2. And this seems a very sound property for the language. It is an obvious property for the language, right? Any sane programmer would expect that from the same language. So how could it break? Actually, the people who were reading the GLS chapter 17 at least once know the answer for which T it breaks. But let's now understand what do we need from the implementation and hardware to actually satisfy that criteria. So in reality, we need the hardware support for atomic reads and writes. If we, for example, we have the 8-byte long, and we have the 32-bit platform which cannot operate on the 8-byte data types, we will have to split the access in the smaller chunks, right? Well, 32-bit x86 is actually simpler because there are all sorts of abominations in the instruction set architecture that can help you. 32-bit ARM is more complicated. Also, you have memory subsystem requirements. For instance, crossing the cache line usually loses the access atomicity. If your value is not, if your 8-byte long, for instance, is not aligned by 8, and you cross, and it, its upper word lies on the one cache line and its lower word lies on the other cache line, then read of that value is probably not atomic in even on x86. All right. So as the compromise, spec says that reads and writes are atomic for everything except long and double, which should be 64-bit in any other implementation. And if user wants to regain the atomicity, he or she has to put the modifier volatile before the field declaration. Thus, it will demarcate that he or she understands, that there is the associated performance penalty with that access. And it is actually reasonable because back then, when memory model was specified, most of the hardware was actually 32 bits. 64-bit hardware was not ubiquitous at all. So it was a sane thing to do. If we required the atomicity for long and doubles, then we will have performance penalties for all the hardware right now. Very often, misaligned access loses atomicity. I actually had the example a week ago on my Twitter. How can you lose? Oh no, that was performance. Yeah, but I can show you today how you lose atomicity when you give misaligned accesses. So implementations are forced to align fields. So for instance, if we have the object A and we have the long field F there. So if you look at the layout for this object, which you can conveniently get with the OpenGTK Joel tool, you will see that the field F actually lies at the offset 16. The objects themselves, in hotspot at least, are aligned by 8. So that means any object which has this long field F, or the access to F would be aligned by 8 as well. That, by the way, you can notice there that that means in the object layout there is the alignment padding gap at the set 12 with a size 4, which means if you try to count, for instance, the object instance sizes by summing up the what you think is the field sizes, it's probably not something that happens in reality. So implementations have to align fields to gain this access atomicity guarantees. So I actually have an interactive quizzes here, but since we have 32-second lag between what I'm talking and what you can reply on IRC, I will just back off for a few minutes, well, not for a few minutes, for a few seconds for you to think about it. So assume I have atomic long. It's there, it's initialized, and first thread sets -1 there. And in 2 complement 4, -1 is all ones there, right? And the second thread tries to read from the atomic long and prints the value. So what could this example print? Think about it for a minute.
So Alexei, I think we should ask Oleg.
Oh yeah, Oleg. So what
that is totally unfair. I just wanted to suggest to ask Simon because he's a more appropriate candidate. But like I think that we can read, let's say 0.
Yes.
Yeah. And let's say we can read -1.
Yes. Can we read anything else?
Well, I don't think that, right. I don't think that we can read like something in the middle between -1. So -1 is all bits set to 1, right? So yeah. And since we're talking about long, which is 64 bits, so it would be possible to imagine that this write is not atomic, so it would write like in 2 chunks. So maybe on some implementations that kind of are broken, maybe that we could read like the long, which is left bits of that long are set to 1, and right bits are set to 0, or the other way around. So like some intermediate number.
All right, but the implementation says atomic, so people reasonably expect that the reads and writes there are atomic.
Yes.
So the question is whether we can read this, torn value, right?
Yep.
And most people said, well, geez, this is the atomic class. Is this one of those special classes which VMs treats specially, and so it will, try to do atomic things there. But it turns out that there is no magic. The long there in the atomic one is just volatile long, and by language spec, you are guaranteed atomicity on accesses. So you cannot print anything else than 0 or -1 there. And it's not some magic within the atomic long. It's just the language provision. All right, moving on. Yes, I will do this diversions into the other languages. If you don't understand those, that's completely fine. So value types. Everyone thinks they want to have value types, right? Do you guys want to have value types?
Yes, we are very excited about that.
Yeah. And among all the beauty that you can you will gain, you will also have the interactions with memory model. So, for example, in C and C++11, you have the STD atomic, which actually says that reads and writes into that atomic are actually, atomic by definition, and it's also atomic for any plain old data. So if you have a struct which with all these fields there, and you set the struct in one thread and read the struct in the other thread, you have to guarantee atomicity there. So how can I accomplish that? My implementation is forced to somehow do this atomicity thing, and no hardware that I know of can do the atomic reads and writes of 104 bytes. So what the implementation has to do?
Well, obviously you should guard this thing with locks or something to...
Yeah, locks or caches or all this stuff. And the really tricky part is that the language, the C and C++, they allow separate compilation. So it is plausible that the first thread object code would be compiled by one compiler, and the other thread would be compiled by the other compiler. And then the linker is faced with the seemingly, well, not impossible, but very hard task to actually match what are the implementations of atomic on the left and on the right. Thank God it's not the issue for Java, because we compile just in time and we don't conserve, we don't have this issue here. So in JMM 9, which is called 9 because it is targeted to 9, although I'm not sure it will be there. We try to reconsider things. That exceptions for long and doubles were pragmatic in like 10 years ago, when we have the ubiquitous 32-bit machines. But now, 10 years later, we have lots of 64-bit machines, and we have only a few 32-bit machines. Well, the Internet of Things will probably revisit that, but the server market actually has most of the machines are 32-bit VMs. So the question is whether we want to drop this exception, whether we want to say that all types are atomic now. And the problem with the current spec is that we have to use keyword volatile because we have a very short list of keywords that we can use, and the keyword volatile is really overloaded with meaning. And if I just want the access atomicity for long or double, then I have to put volatile there because it's required by spec. Even though if I run on 64-bit machine, I will have the de facto atomic access anyway. But I will pay for another semantics for volatile with memory barriers, because volatile also means ordering, which we will talk later. So I have a few performance examples here, but let's skip them right now because we have a limited time. We can back it up there, but you have trust me that the volatile barrier costs are actually quite significant in many cases that we might want to reconsider whether we want to put them do the longs and doubles volatiles or not. I actually have the blog post which explores this in depth. All right, word tiering. I can skim briefly through IRC. I think there's no questions there. Yeah, some people feel too stupid to give us my thoughts. That's expected.
And
that's very modest of you.
Yes, I am. I am a very humble person. All right. Yes, if we don't have if we have a 32-bit VM and we imagine if we want to have 32-bit atomicity, then yes, we can use the instruction set extensions to do this kind of stuff. For instance, x86 32-bit actually uses x87 FPU instructions to load and write atomically 64-bit values. So there are workarounds for this kind of thing. All right, I think that addresses the questions on IRC. Let's go for the word tiering. And word tiering. What is the word tiering? This is a more complicated example. Suppose we have the array of t, and t is some built-in type. And we initialize the array elements at positions 1 and 2 with some value v0. And we have 3 threads now. And the first 2 threads are writing v1 to the corresponding indices in the array. We wait for those threads to terminate, so we are reasonably sure their effects are committed to memory or whatever formalism you have in your head. And then you wind up the other thread, which tries to read the values from this array. So the question is whether this assert could fail or not. Oleg, what do you think? Could it fail in Java?
Sorry, I think I was muted. Yeah, I don't think that the array access are atomic in a sense that we do have atomic arrays classes in Java. So I would expect that we can encounter a situation where reads are not in sync.
So it's really simple to confuse this with the atomicity. It's not really about atomicity. It's about the independence. It is about the independence of operations on the particular language elements, whether it's fields or the array elements. So atomicity is not here. It's not on the table. So OK, let's assume that as the same developers, we would expect that the same language implementation will provide us with this guarantee that you will read either, you will read v1 from both elements in the third thread. How could it break? So why can it break? It turns out that we need the hardware support for independent reads and writes. And if we don't have that support, we have a problem. So for instance, if you have a Boolean which fits in the single bit, but you can only read and write 8 bits on the machine without other trickery of interlocked operations or something like that, then you have a problem because you cannot read and write that single bit value without disturbing the adjacent elements. You will have to read the entire chunk into the memory, into the register, flip the bit or modify some part of this byte in the register, and then write it back. If you have 2 threads that are doing this concurrently on their seemingly independent positions, and if these chunks are interlapping for both threads, one of the threads can actually destroy what other thread did. This is what word tiering is all about. We just turn the word that we read and write into the memory, and this assert could fail, right? This is what's there in reality. JLS takes a firm stand on this. It says that word tiering is prohibited, period. If you have 2 array elements or 2 fields, and you read and write from the different threads in those fields, the reads and writes are undisturbed. There is actually a funny discussion on the GMM dev list from, I don't know, 8 years ago now, and Bill Pugh, who is widely known by find bugs, but he was also the spec lead for GSR 133, which is the Java memory model update. He actually said that if the decision of, and I'm quoting loosely, it's not the strict quote, if the decision of this expert group would be allowing the word tiering in the Java language, then we should disband the expert group right now. Because people who are chasing the bugs due to word tiering are not happy at all. I actually chased a word tiering bug once in C application for 2 days straight, and it's not fun. It's not fun at all. So Java prohibits word tiering. That, by the way, means that if we have the booleans, which again I can fit in a single bit, the reasonable implementation should allocate the entire byte for the boolean, because that's the minimal, chunk that I can read and write. This, value independently. All other types are okay. So if you run the JOL tool, and it will try to detect what is the data type sizes there, you will see that two scales there, and the scales are the field sizes and the array element sizes for the data types. And from left to right, it's reference, boolean byte, short char, int float, and double long. And you can see that only a byte actually wastes, only a boolean wastes space. All other data types are actually fitting their domain nice. All right. So let's get back to this example, to another example. This is, I did the example before with the array, and I told you that the word tiering is prohibited. But now let's see, we have a bit set. And Oleg actually knows the answer on this because he used that example in one of his posts. So Simon, you're up for answering this. So you have the bit set, and you have two threads which set the adjacent bits in this bit set, and the third thread which tries to print the values of these bits after the first two threads terminate. So what could it print? Bit set get returns boolean, so you can print either true or false. So what would it print?
Okay.
Can it print true?
Yeah, so it could print true.
Can it print true false?
It could print true false. Yeah.
But I just told you that the word tiering is prohibited, and what you're telling me right now that the word tiering is allowed. How to go with that?
Yeah. So I'd have thought it could print true false, but not false true.
Actually, bitset is tricky because it actually packs the bits into the integer arrays and does the masking operations on those integers in order to have the dense cracking for these bits. And in this fashion, it actually breaks from the provisions of memory model, and you cannot expect, the absence of word tiering there. The implementations, the bitset implementation sets you up for that. It actually avoids, well, not avoids, it makes it legal by saying in Javadoc that you cannot use bitset without synchronization. So if you use the synchronization over the bitset in this example, then you will only get true. But if you don't, if you do the RACI updates of bitset, then you can get either true false, or false true. The complicated question is whether you can get false, and I will leave that as the exercise for the reader there. All right, so I am reasonably sure it could print these three tuples, and I have the runnable example if you want, and if you have time after the talk. All right, bit fields. Everyone thinks they want, well, not everyone, but most people that I'm talking to think they want a generic way to control the object layout in Java. So in C, for instance, in the struct declaration, you can say that if I have the field in struct A or B, I can actually say how many bits to allocate for the particular field. So I can do the struct in which A, is the 7-bit field and B is 3-bit field. And if I have the code in which I have the struct T in one thread, I write 42 into A. And in other thread, I try to read something from B. if my language disallows word tearing, it has to do some magic there, because my hardware does not have, well, most hardware does not have operations that could read or write 7 bits independently. So if my language guarantees the absence of word tearing, and you have the way to control the object layout and the field layout in the object, then implementation would have to face the music on every axis to A or B. And if you don't have the hardware support, you will have to resort to locking or atomic thing or something like that, which probably departs from the C philosophy that you will have the raw hardware performance for most of the code, right? So C and C++ actually says that if you are using this bit scales there in structs, then you are on your own. You don't have any guarantees about word tearing. All right, in JMM9, we know that word tearing, the absence of word tearing is the same requirement for the language, and so we will not do anything with it. It just stays there. It is a plausible thing for the language to have, and it will stay there. All right. Now we are going to the meaty part of the spec, and this is SC-DRF. Don't be afraid if you don't know what this words means, what these letters means yet. We will gradually build up our intuition for it. So what do we want as the programmers? If we have a multi-threaded programs and one thread executes operations A, B, and C, and other thread executes operation D, E, and F, we as programmers, as humans, we would like to think that this program executes in some sane order. You know, the operations within one thread should probably execute in the order defined by the program itself, right? Because, well, otherwise you cannot debug this thing. And we also like to have this simple mental model of, you know, operation system scheduler will context switch our thread and, you know, pass the control to the other thread, and that other thread will pick up where it had left, right? So it's for us humans, it's very easy to reason about the program that executes every operation within the thread in order, and thread executions just interleave. You don't reorder anything there. They're just interleave. And this is a very simple reasoning, so that Lampert actually defined this as the sequential consistency. And the definition for sequential consistency is as follows, and this is a direct quote, that the result of any execution is the same as if the operations of all the processors were executed in some sequential order in the order of each blah, blah, blah. Yeah, so this is exactly what we want, right? We want to think that program had executed in this particular fashion. And this is a very tricky definition, because the main part of this definition is this 5 words. The result is the same as if. We are not actually required to execute the code in sequential consistent fashion. We just need to provide user with the result, which can be explained by some sequential consistent execution. And here is the example. We can change the program in whatever fashion we want, provided there is a sequential consistent result. So if we have the program on the left, which has the 2 global variables, A and B, and 2 threads, first thread writes 1 to A and prints B, and the other thread writes 2 to B and prints A, it is possible, without breaking sequential consistency, to optimize this program to the program on the right, which will just unconditionally print 2 in one thread and unconditionally print 1 in the other thread. Because there is an obvious sequential consistent execution of the program on the left. It's as if first you executed A equals 1 and B equals 2, and those values commit to memory, and then you just read those back and print them. So the behavior of this optimized program is the same as one particular behavior of the program on the left. So given that, let's assess whether we can do these optimizations or not. It seems simple, right? It seems simple to do this kind of optimizations. So if we reason about what optimizations are plausible in the code, we can try to think about the reorderings of the operations of the program. So assume we are the compiler and we want to compile the program on the left into something. Well, suppose that I am, as the compiler, for some arcane knowledge that I have, want to reorder the reads of A and B. Can I actually do that without breaking sequential consistency? Can I do this reordering or not? I'm just compiling this one thread. Oleg?
I think you can do that freely.
All right. So let's assume we did this kind of reordering in the one thread, and we keep the other thread untouched in the original program. So the program on the left is the original program, and the program on the right is the modified program that we had compiled, right? And we reordered the actions in the first thread. So if you execute the second program in the, in this waterfall order as is depicted here, you will gain this result. First, you execute R2 equals B, and R2 is then 0 because no writes had happened. Yet then you assign 2 to B, assign 1 to A, and then finally you read R1 to A. And so this gives you the result of this tuple of R1, R2 is what?
1, 0.
1, 0. All right. Is this a sequential consistent result for the original program? Well, if you look at the program on the left, you can actually reason about this quite simply. If I'm executing this program sequentially, that means that either R2 equals B or A equals 1 should be the latest statement, the last statement in my execution order, right? Because it is the last statement in the thread, and there's no reordering within the thread. So if I have R2 equals B as the last statement that I executed ever, then I can only have the tuples that have something 2, right? Because I am obliged to see the write to B, because it will happen if the read from B is the last statement. Conversely, if my last statement is A equals 1, I have to read, my results has to be 0 something, because my read of A that happened before could only read 0 because it couldn't observe A yet, right?
That's true.
And modified program yields 1.1, 0. And this is not a sequential consistent result. You cannot explain that result by sequential consistent execution of the original program. So this optimization of just plainly reordering 2 lousy reads there, which seem to be very intuitive optimization, actually breaks sequential consistency. And you have to analyze what happens in other parts of the program to see whether that reordering will break sequential consistency or not. Whether it will, generate the surprising results for the programmer and make his or her head explode. So sequential consistency is a very appealing model for humans, right? We would like to have the sequential consistency in our programs. But for the implementation, it's really, really hard to tell what transformations are safe, what transformations are not breaking SC, what transformations are not yielding new surprising outcomes in the program. In theory, you can make this global meta-optimizer application, a compiler or implementation, which will be able to analyze this, analyze all the uses of all the variables in the program and see that if I reorder this particular reads or this particular writes, nothing bad is going to happen. in theory, it works. In practice, however, both runtimes and hardware are GMO-free. We could not yet build such a global meta-optimizer. So if we are not able to do this global meta-optimizer things, that means that if we are enforcing sequential consistency in the language, we effectively forbid any optimization. If we forbid even the simple reorderings, we are forbidding most of the optimizations in the language. And you can back it up to this, trade-off discussion there. So you can please your programmers and provide them with the same memory model, but then you will have a lot of trouble providing the high-performance implementation for this language. It also gets worse in the sense that hardware actually reorders by itself. We can, if we require sequential consistency in the language and we make our implementations to not reorder anything, so we will do our part there. If we run on the real hardware will reorder the operations for us. And this is the nice table from the Wikipedia, which will say that there are platforms when you can actually reorder a whole lot of things. So if I have the language that requires sequential consistency, not only I have to break the reorderings in the compilers and thus breaking the optimizations in the compilers, I have to also instruct hardware not to reorder stuff, which means probably the memory barriers after each memory access, whether it's read or write, which could not be fast. Right? So we need a weaker model. If we are careful enough in this model, then many profitable optimizations would be allowed, and most developers would still be able to figure out whether their programs are correct or not by learning these rules. And maybe the language spec would be still actually readable. So before we go to the formalism of GMM, let us have some few basic definitions. We say that the two memory accesses conflict if they use the same memory location and at least one of the accesses is right. And the program contains a data race if two memory accesses conflict and happen simultaneously. And the definition, what is simultaneously, is tricky. In this particular definition, simultaneously means that they are not ordered by any synchronization. And racy programs yield surprising results, as we will see later. So for GMM, GMM is the language spec. It has to encompass all the possible things that could happen in the language. And so it could not, provide you with the anecdotes about the program behavior, language and program behavior. It has to specify the behavior of the language rigorously. So it cannot, for instance, say that this particular program transformation is allowed under memory model and this particular transformation is not, because you cannot use that knowledge to reason about the programs at large. So GMM is not reasoning about programs themselves. Instead, it builds the parallel formalism for the entire thing. First, GMM defines actions. Actions like reading something from the particular field or array element, or writing something to the particular array element or the field. These actions are aggregated in the executions, and the executions are bound, are binding the actions with the orders over these actions. It happens before, as you know, one of the most famous orders there. We will gradually build this formalism there. And GMM specifies what outcome is allowed by the language. So it has, you can think about it as you have all the possible sets of actions and all the possible sets of executions, and you have the orders over actions. And the outcome, sorry, I actually puzzled myself here. If I have the execution which fits all the criteria for Java memory model, and it has, for instance, a read from the variable x which reads 1, that means that the plausible program, that the program conforming to Java memory model can actually read 1 from the x. We will see on the examples how it goes. So this is the most twisted part of this talk. Let's go and build some formalisms as they build in the JMM spec. First, we start with the program order. So let's suppose we have this program at the center, which says if x equals 2, then we store 1 to y, or we store 1 to 0, and then we read something from y to r1. So we can try to reason, if we have the execution on the right, which contains 3 actions, read 1 from x, write 1 to z, and read something from y. Whether this can this execution be used to reason about the behavior of this program? And we can say that, and actually spec says that the actions are bound together in some program order, and program order binds the actions that relate to the actions in one particular thread. So this is a valid sub-execution at this slide. Program order is the total order, so every 2 actions within the single thread are ordered with program orders. So for instance, if I actually read 2 in the first action, then I have the next action of writing 1 to y, and then reading 1 from y here. And this is the execution that relates to this particular program. Notice that, and this is the tricky part in the spec, is that if you read the spec first time or the second time or the 10th time, you will confuse yourself into believing that the program order relates the program statements. It doesn't. Everything that happens in JMM has a very thin relation to the particular source code. So here we have the program order, which is total, that the actions on the right are actually totally ordered, but the statements on the left are not totally ordered. For instance, the statement of assignment 1 to y and assignment 1 to z are actually not ordered at all. So now that we buffered this vague understanding of how memory model works, imagine how now I have to let you to imagine this primordial soup of executions, which has all the executions of all the actions constructible in this parallel construction of JMM. Somewhere in the set of these possible executions lies the execution which justifies the outcome for the program that you are now looking at. JMM's purpose of life is to figure out whether there is such an execution. So the first, so we have to select from this primordial soups the executions that we can use to reason about the outcomes of the program. And the first filter from that primordial soup is called intra-thread consistency. It says that for each thread, the order of actions in program order is consistent with the thread's isolated executions. So for instance, if I have the same program and I try to reason whether the execution on the right can be used to reason about the program behavior on the right, I can actually see that the execution on the right breaks the inter-thread consistency. If my thread had actually read 2 from x, it could not write 1 to z. It should be followed with the action that writes 1 to y. So this action, however smart it is, cannot be used to reason about the outcome of this program. So I cannot use this execution to justify that I can read 1 from y and in the last statement. So the inter-thread consistency filters out the executions that can be used to reason about this particular program. This is the only link between this parallel formalism of GMM and the rest of the language spec. Everything else that GMM does, it does structural constraints on the executions itself. How can you relate a particular execution to the original program? It's only about this inter-thread consistency. And this is really the vague part, but we will have to build on this when we will do happens before stuff. You will have to wrap your head around this, and you will probably have to get back to these slides and understand how this works, because this is not a trivial thing, but it's also a boring thing. Now let's go.
Alexei,
Yeah.
Sorry, we have a question about program order in the IRC, and the question is, can you give an example how you would construct a program order of a simple Java program? So, for example, if it's try return x equals 2, and then finally return x equals 1. So what could be the program order of that? And the author of that question is Vladimir Sitnikov. So I think it might be an interesting one. Or we can come back to that later.
Yeah, we can come back to this later. The thing is, the memory model is not constructive, so you cannot. I don't think you can take a program and construct all the possible executions for this. Well, no, I think you can. We can try that after this talk. The goal for inter-thread consistency is to say if I have the execution on my hand, to figure out whether it fits the particular program. So it goes the other way around. You don't usually construct. Only in trivial cases you can construct the program, all the executions with all the relatable program orders based on the original program.
So yeah, so we are talking about actions that reads and writes of particular values, and not just like read like x or read something. So
yeah.
In the program order, it's always read x.
Yeah,
value
program
1.
order is all about the actions. It's defined on actions. It's not defined on the statements. You can think about this as the your program induces the actions.
Okay, good, thanks.
So okay, we talked before that we want to construct a weak memory model, because if we construct a strong memory model where all the actions are ordered, we'll probably arrive at something like sequential consistency for everyone. And while programmers will be happy, the implementations would be very, very disappointed, because you cannot really implement those effectively. So we have to build a weak memory model. And weak memory model is special in the particular regard that you don't order all the actions. Only some special actions are ordered. And the special actions in JMM are called synchronization actions. And those are actually listed in the Java memory model spec. And I listed them here. It's the volatile reads and volatile writes, locks and unlocks of monitors, synthetic actions, first and last actions and threads, and all these actions that detect the threads have terminated or start the thread. These are actions that are actually ordered. Let's see how they are ordered. And I have to unload on you the formal definitions first, and then we will talk how they actually work. So synchronization actions form the synchronization order. So they are bound in this synchronization order. Synchronization order is the total order, which means that every thread observes synchronization orders in some order, and it also means, and we will also see later that that's the only cross-thread order that has to be total. Synchronization actions order in program order is coherent with synchronization order itself. And this is the murky definition, but you will see this thing is actually really smart, because it says that the synchronization actions within the single thread are observed in program order. And synchronization actions, sorry, globally actually observed in the order of particular single thread. And there is also a synchronization order consistency, which says that the all reads in synchronization orders see the last writes in synchronization order. This is what you will actually read in spec. And this gains you nothing, right? It's just a gibberish when you first read it. So let's see how it goes in the examples. Let's see this particular simple example. It is usually called the Detector example because it is the part of the construction which is called the Detector log. So for example, we have this x and y, which are volatile ints. And first thread sets the int and reads the other one, the other int, and another thread goes vice versa. So think about it. What pairs of R1, R2, and R2 are allowed? Oleg?
I really wanted to give this question to Simon, but let's see if I get it. So we do have volatiles, right? And so actions on the volatiles will be synchronization actions. I think we saw that 2 slides ago, no?
Yes.
So yes, so we can read 1-1 easily.
Mm-hmm.
We can read. I don't think we can read 0-0. And we should be able to read 1-0-0-1.
Why can't you read 0-0?
I have a gut feeling, and I think I saw some examples somewhere. But to reason about that, so we have to like threads. So thread 2 observes thread 1 actions in the program order, since those are those operate on volatiles, so those are synchronization actions, so they should comply with synchronization order. And I think I lost my idea here. But yeah, I'm fairly sure we cannot read 0-0.
All right, let's see what spec has to say about this. How do you reason within the spec about the behavior of this thing? So this program obviously generates the executions which has 4 actions, because you don't have a complicated control flow here. It just generates these 4 actions. And the actions are writes of x and writes of y, and read of y something, and read of x something. We don't consider any other executions because those would by construction be not inter-thread consistent. Only the execution which has these 4 actions like that would be inter-thread consistent. All right. So how do we proceed with this? First, we know by definition of program order that these 2 pairs of actions are bound in program order. But this doesn't really give us anything yet. As Alex says, that all actions around x and y are volatile, hence those are synchronization actions, so they are in total synchronization order. However, you can lay this order in a few different ways. This is the first way you can lay this order. So you first have write 1 to x, then read y, then read x, then write y. Can you put the synchronization order like that? Oleg?
Well, yeah, but like as the slide says, it is not consistent with program order, so...
Yeah, so you can, by construction, you can actually put the synchronization order like that, but this definition would be not, it will fail the consistency rule, which says that synchronization order should be consistent with program order. So I cannot use this execution to reason about the outcomes of program. If I could actually reason that I read 0 in Y and I read 1 in X, right? Yes.
Yes.
But since synchronization order and program order is inconsistent, this execution should be thrown away. Let's try other thing. Can I put the synchronization order like that?
Yes, you can.
Yeah, the slide says you can. Yeah, and synchronization order is now consistent with program order. And synchronization order consistency, which is the third rule in my slab on the slide there, says that the reads of the particular locations should observe the latest write to that location. So if I want to figure out what should the read of X get, I can just walk back in synchronization order until I reach the first write to X and figure this out. So in this particular execution, what is the value of read X? Oleg?
You should read 1, because if we travel through sequential order back, we will see the write of 1.
Yes, and in Y, we can only see only 0 because we cannot yet observe the write to Y, which is after us in the synchronization order.
Yes, so we will get 0, 1.
Yeah.
And if we reverse the line of the synchronization order, then we'll get the opposite.
Yeah, let's do the third one. Let's arrange the order like this. It is the synchronization order is consistent with program order. And because of the synchronization order consistency, again, what should I read in Y and X?
You read once, because reads or both reads actions are after both writes.
Yes. And now we build a simple intuition from these rules. And the simple intuition goes like this. Notice that synchronization order consistency means that I have to read the latest write in this particular synchronization order. And because synchronization order is consistent with program order, that means I have to read the values that I've written in this thread or some other thread if my synchronization order spans the thread boundary. So if you look closely at these examples, you will figure out that it seems like if all my actions are synchronization actions, all the actions within one thread are executed in program order because that's what constraints are doing for me. And if I ever switch from one thread to another, I pick up where I left. So this observation actually builds up to the high-level observations that synchronization actions are sequentially consistent. So if I only have the synchronization actions in my program is sequentially consistent. So I can have a simpler reasoning about this program. Like the reasoning I already did with the example about synchronization, about SC transformation. If actions that this program generates are in some total order, that means that the actions for the last statements in each of the threads are coming last in the synchronization order. So you have, and if that happens, one of these reads should observe the write, which means that the case when you read both zeros is forbidden. There is no total order which can bring you 0, 0. And this is a really interesting property of the spec. I can show you that on the more complicated example, which is called independent reads of independent writes, or IRIV. When you have 4 threads and you have 2 global variables x and y, and the first 2 threads are writing once to x and y, and 2 other threads are reading the values from y and x, but read them in the reverse order. If you build all the interleavings of these threads, you will figure out that any execution that yields that particular quad result, when I read, once in R1 and R3, and then suddenly I read zeros in R2 and R4, as if I observed the writes to X and Y in different order, is forbidden by JMM. It will break either synchronization order consistency or synchronization program order consistency. And this is the very nice property of the spec. And Hans Boehm actually said that it's so nice that if you have the program, then you have the races around the program. And if you sprinkle enough volatiles around the program, eventually it will come to the point where all the critical actions that you have in your program are turned into the synchronization order, synchronization actions, sorry. And those are totally ordered, and you can reason about your program as this, sequential, consistent interleaving of the program statements. So yes, you can when you throw volatiles at the program, it becomes more correct. It cannot become less correct. So synchronization order consistency provides this totally ordered skeleton for the program. This is the only total ordering that you should have between the threads to actually construct the memory model. We will now quickly build up to what happens before. Synchronization order alone is not enough to provide the weaker model. We only care about synchronization actions at this point, and we say nothing about non-synchronization actions. So it's all or nothing. Either you turn all the actions into the synchronization actions, and then you have the very strong memory model which prevents optimizations, or you just blindly cover your eyes and don't care, stop caring about non-synchronization actions, and they just float around and break your programs. Neither of the options is really appealing. So we have to have some another weaker order which binds synchronization, non-synchronization action operations. So let's first look at this example. So we now have the example when we have the global variable x and the volatile variable g, and this program which says sets x to 1, g to 1, and reads g first and then x first. Think about it, whether the result of 1, 0 is allowed or not. Alec.
Well, if we talk about JMM, then it shouldn't be allowed. What, 1, 0? 1 is G. Yes. So if we observe the write of G, then we should observe the write happened in there. But since you're asking tricky questions, yes, I'm confused.
Yeah. So let's suppose we are only using what we have built so far in the memory models. We only have the synchronization actions and synchronization order. So we only order the actions, synchronization actions, which are only actions around G. We can build the execution which has, read and write of G ordered in one way or the other. But the reads of X and writes of X are not ordered at all. So we can have a plausible executions that read either 1 or 0 if we only use the constructions that we have right now that only cares about synchronization actions. We have to add something to the model which will order X's here. Okay. So yeah, there are plausible executions which can read either 1 or 0 here at the R2.
And just to reiterate, we don't want to use program order here because that will deny too many optimizations, right?
Program order does not at all tell you, yes, it's not at all tell you what you can actually read. It only So far, program order only was used to enforce a particular suborder for synchronization order. It's not in itself provide any,
Okay, so we stepped away from that, and now we are considering just synchronization order. Good.
Yeah. All right. So program order is not usable in our example because it, by definition, does not order actions in the different threads. It only orders actions within the particular thread. We need some order that spans thread. But so far, we only have synchronization order, which is total. And again, if we turn X into the volatile, we will, break optimizations because we will arrive at the strong memory model again. So we have to do some other weaker order. And in spec, you first build the suborder of synchronization order, which is called synchronizes with order. This is the suborder's constraint for the concrete reads and writes, and we will see in the example how it works. And this is how we reason about this example in the full spec. So suppose we have this particular execution here. It has 4 actions, and if we are talking about synchronizes with order, there is no synchronizes with order between the write of G and read of G yet. Because in this particular example, the read of G does not observe the write to G yet. If it was observing this write, then we will have the synchronizes with order. These actions right now are bound with synchronizes with. This gives us the inter-thread semantics between, this read and write of G. Now we have a program order for the remaining actions. But this thing does not really constrain us yet from reading either 0 or 1 in X. So what they are bound in this, arrows there, it doesn't really mean much at this point. We have to enforce some constraints there. Before we enforce that constraints, we do this tricky thing. We say that we will do the union of program order and synchronizes with order, and we transitively close it, and then that will bring us a happens before order. See how we had the inter-thread semantics given by program order and the intra-thread, and between the thread semantics given by synchronizes with order. If we do the union of these orders and you close it, then you have happens before. But even if I have this happens before order right now as constructed, it still does not prevent me from reading 0 or 1 in X yet. I have to define something on happens before. So there is the rule which is called happens before consistency, which says that the reads either observe the immediately preceding write in happens before to the same location, or something else via the race. So if I have this execution here, the only execution that, well, not the only, but one of the executions that happens before consistent is the execution that reads 1 from X. Because I can step back and happens before order and arrive at the latest write to X, which is 1. Happens before order is also tricky because it allows to read something else via the race. We will see about that in, I think I will pass this guy here. I will pass the formalism, and I will say that this happens before consistency is actually something that after you build the order on the execution, you can actually see that if I read the particular values from the reads, is this execution happens before consistent or not? And let's redo this example again. So we have the same example. Let's analyze it with the happens before consistency rules. So this execution, where G observes read from G observes the write to G. And so I have synchronized with, and when I transitively close it, I have happens before. And if I have the execution which reads one from G and reads one from X, this execution happens before consistent because both writes actually observed the latest writes in happens before. This guy, surprisingly, also happens before consistent, because if I wonder whether the particular read of G or X can read 0, there's nothing preventing me from reading that, because I can read something else via the race. I can read some else unordered write. This guy also happens before consistent, because again, nothing prevents me from reading 1 in X, because I'm not obliged to see the write to X in the other thread, but nothing prevents me from doing that as well. And this guy happens before inconsistent, because if I analyze it, this execution under happens before consistency rules. If I look at the read of X and try to figure out whether it can read 0, I can back up in my happens before order and realize that I should have read 1 there. So I cannot use this execution to reason about the outcome of the program, which translates to this particular result of 1, 0 is forbidden in Java memory model. Let me back up a little. If you read the spec, you will actually read the quite complicated paragraph there, which will say that the happens before consistency is quite complicatedly defined. It is written in the plain English there in the spec, but I will use the more concise formalisms there. So it's actually said that if I have the set of all program actions, which is A, and I have the function W, R, which returns me the write observed by R, happens before consistency says that for each read in my action, in all the program actions, it is true either of those things. Either the write I am observing with this read is not ordered with the read itself, and this is by definition is the race, or I observe the latest write in the program order to this particular location. If the second part is true and I observe some read in the happens before order before me, the second part says that if I can only observe the latest write in my happens before order. You will have to revisit this, I think.
Sorry, you just typed something, so Hangouts just ate the last sentence, I guess.
Sorry, yes, it was, yeah, I backed up the slides. So, okay. So the happens before provides you with the orders for non-synchronization actions, non-synchronization actions. And SC-DRF says that you have the strong requirement, which is called SC-DRF. It says that the correctly synchronized programs have sequentially consistent semantics. It actually means that if you don't have races, which means all the reads and writes are ordered either by synchronization order or happens before order, that means that all the reads see the properly ordered writes, and you know what exact writes you see in the executions. The outcome of the program can be explained by some sequential consistent execution of it. And there is the formal proof for that, but there are 2 intuitions around this. The local operations, which I do within the threads, are always almost always have the outcomes explainable by sequential consistency. No matter how I reorder them locally, if I don't mess with the global data, I'm fine. And the second part of this intuition is that if I do the operations over global data, if those actions are ordered, which means that I use the synchronizations around them, then I will define the order over the actions which are, visible from the different threads, and those are also sequentially consistent because those are also ordered either by synchronization order or happens before. Right. And this is a really hard part of the spec, and our heads will explode if we reason about that all the time, because you will actually have very hard time figuring out for the particular programs. So most people derive the high-level concepts from that. That example that we built up with the plain X and volatile G actually says that if we observe this, volatile G as 1, we have to observe the preceding writes. It can be generalized in this publication idiom. If you have the one thread which does writes, and then it does the synchronization actions, say writes 1 to the volatile variable G, and then other action that observes this written value. So you have the happens before, you have synchronized with and happens before bridge between these two actions. Then you have the happens before between all the preceding writes on the left and all the subsequent reads on the right. You can, many people actually also use the terms release and acquire. They say as if the write on the left had released all the memory state that this particular thread had done, and thread on the right had acquired that state, and so all the writes in the first threads are visible. And because of the way it's specified in the spec, this only works if you do these actions on the same variable. So you cannot write to the one volatile variable and read from another and think it will give you the happens before. Works only if you had observed the actual write on the left. So if, for instance, in this example, I read 0 on the right, there is no synchronizes with, therefore there is no happens before, therefore this blows up spectacularly. And those are also paired. You cannot, make the release on one side and then by some weird set of rules that you had read on the internet, speculate that all the writes are somehow magically committed to main memory, and somehow magically second thread, reads that state from memory, and all is fine. It's not working that way. So let us get from that. Now that we have built this recipe, let's try to use it in this particular example. So for instance, I have this class C, which has the value val. It's just a wrapper around val. And I have a setter and the getter. And setter and getter are synchronized. And then I profile my application, and I realize that the setters are actually, the getters are actually very hot in profile, and they are the performance bottlenecks because those are synchronized. So I submit the bug and say, well, we have to optimize the getter. So what do we do to optimize performance here? Surprisingly, many people will argue like this. Well, it's just the write to val. We will do this write under synchronization. It somehow magically flushes the caches, and so we can just treat it in get, and we will have everything in order. So they do something like this. They just drop synchronized from getter and say, well, this is safe without synchronization. Is it really safe without synchronization? Simon?
Simon, are you there? I can maybe take
Sorry, yeah, I am, but I was doing something else and I have 100 windows open. Sorry. Oleg, I'll pass to you for this stuff.
So, Oleg, all right. Is it safe, Oleg?
It shouldn't be safe. So to be safe, we need the actions between. So imagine we execute sets and gets in different threads. So we have to bind the actions with some order between threads. So that must have go down to some synchronization action, and synchronization actions or actions on volatiles. So
you actually have synchronized, and when you exit synchronized, you have the monitor unlock, which is by spec, is the synchronization action. So you can reason that the first thread which sets will do the synchronization action, the release action as we built in the recite before. So
yeah, but we need a pair of those. We need not only release but then acquire as well.
Yes. So we need acquire. So some guys do this. They say, well, yeah, obviously we need acquire here. So here is the volatile int variable, which we read and store somewhere, but that's not essential. This is the acquire. We have the release and synchronized in setter, and we have acquire with the volatile here. Does it work?
We do have a pair of release and acquire, but they do not operate on the same variables. So.
Yeah, they are not pair actually. They are just independent synchronized actions. In the conservative implementations of GMM, like in Hotspot, that will probably work, but it's not coding up to spec. This is coding for the implementation. So this is not safe GMM-wise. It's safe for one particular implementation of GMM. So how do you solve that properly?
Well, I would put volatile on the value itself.
Yes. So this is how it's safe, right? You put volatile at vol, and now you have the release action when you read when you write something into vol, and you have the acquire when you read from vol in get. So the interesting question is whether you can drop synchronized in setter now. Can you?
Well, if I drop synchronized in setter, then I will lose the being able to write just one value. So if two different threads will set something, they both will observe nulls, and one of those set operations will kind of overwrite the other one.
Yes, so you need mutual exclusion actually. Volatiles do not provide you with the mutual exclusions. So you have to keep synchronized there. All right. At this point, I think we have to make a break. It's actually took longer than I expected. So let's take a 5-minute break, and we will restart after that.
5-minute break, great.
I'm on IRC.
Simon, do you have any idea how to organize and how to use this 5-minute break the most? So Alexei probably just wants to drink some water and maybe, I don't know, relax a bit without talking. But
so yeah, I can tell you a few things that are coming up in the virtual jug over the next month or two. We've got a few programs that we're hopefully looking to expand or start over the next few months with the virtual jug. The first one, let me write them down so I don't forget. The first one is the book reading club, and this is something that I kind of crowdsourced some book ideas with people in the London Java community. And if anyone's interested in starting up with this with us, we're gonna be sending out some information about it probably this week. And the idea of this book club is that we will have someone running this, which is going to be a guy called Roberto Cortes, one of my friends from Portugal, and he's going to be running this. And we're going to choose a book collectively as a user group. We're going to use a poll rather than emailing on the mailing list. And the idea is we choose this one book, which we'll hopefully be able to get at a discount from the printer, and we're gonna go through chapter by chapter every week or two. We're gonna have experts come in and talk through it, and rather than look through, say, a certification book or something like that, we're going to be looking through best practices. So that's one thing that we've got coming up really soon. The other is later this month, I'm going to be at a conference in Germany in Phantasialand, which is a roller coaster style theme park in Germany near Frankfurt. And we've got a couple of sessions which we're going to run as live sessions on the night hacking stage at JavaLand. We're going to do one around the OpenJDK, so if people actually wanted to start hacking around with the OpenJDK, we're going to give you all the necessary information and tools that you need to do that, including locations of VMs, so you can literally download a VM, have a little hack, run the build through that VM as well, and play like that. And we've also got one on some of the new JSRs which are coming out, so we're going to get 3 of the JSR leads up on stage to tell us what JSRs they're working on and what we can actually look forward to in future versions of Java, and that's both, I guess, Java SC and EE. The third thing I wanted to mention is actually some of the podcasts that we're doing, and this was half interesting on the list, half spammy, but it was good fun to get people talking. And we're going to do some podcasts in a couple of different ways. It sounds like some of the sessions that we run live may not be suitable for a podcast. So, for example, some of the examples that Alexei has been showing today are hard enough when you actually can see the code on a slide on your screen. So doing it on a podcast will actually be impossible. But some of the interviews, we're going to be interviewing Alexei tomorrow. He's going to have some really interesting information, I'm sure. Understanding whether Alexei prefers puppies or kittens, whether he's a Mac user or a PC user, those kind of things, all the important points. Those kind of things are going to be really easy to listen to on a podcast. So things like that. And also, since the Java Posse, I don't know if many of you have heard of the Java Posse before, since they kind of split after maybe 10 to 15 years of awesome podcasts, we're thinking about maybe doing something like that as well. Perhaps a monthly one where we can start talking about the sessions that we had in that month, and then maybe some news around the month. So those are some of the things that we're looking at over the next month or two. As I mentioned, you'll get some more information about the book reading club. So if you're interested in that, we'll be deciding upon our first book that we're going to be doing in the next week or two. And that may even be announced at our next session, which is next Wednesday, I think. Yeah, Wednesday the 18th on modularity in the cloud. And then there'll be plenty of time for everyone to buy their books, get them shipped to you before we can actually start reading them. One final thing that I will mention is we are growing massively. We've currently just passed the 3,000 mark. So I think we're at about 3,060, maybe 70, something like that these days. So it's really great that we've, as a community, just over a year old, over 3,000 members. So congratulations for being part of an awesome community. Thank you everyone for sharing. If you haven't shared, please do go on Twitter and Facebook and tweet about how cool the community is. And it's great to have so many people, so many members. So yeah, those are the 3 things I had. Have I padded enough for rest breaks and for Alexei to have a drink of water?
Yeah, I think we can get back.
Excellent.
All right. So one of the things that the model allows is the simple set of rules that implementations can use to do reorderings, and that that class of optimizations is called Roach-Mattel. And Roach-Mattel, if you know what it means, is the cockroach trap, when the cockroaches go in and never go out. And you will understand why it's called that way in the examples. So suppose we have the program which yields this particular execution. When you have just the plain fields X and Y and you have the guard variable. So for instance, we have the actions which write X to 1, releases G, meaning writes 1 to G, acquires G, meaning reads the actual 1 from G, and all this stuff around. So can a compiler produce a program which will generate the execution in which the write of Y, or write of 1 to Y, will be reordered before the release, or not? Actually, if you can reason that you can move the write of Y before the release, because the read on the other side in any other program is not obliged to see that one. It can also read something else. But if you put the write into the happens before order, you will just force that read to read 1. So you are not introducing new behaviors. You're just constraining the set of the possible behaviors there. So this optimization is plausible. Conversely, you can probably move the read after the acquire, because in the original program, that read could observe the write of X on the left, or it could skip that because it's just the read through the race. If you put it in the happens before order, it will have to read 1. So again, you're not introducing new behaviors, but you're just using the one particular outcome that is plausible in the original program. So if we take these two things together and we remember that release and acquire is, maybe it's volatile read and volatile write, or maybe acquire is the monitor enter and release is the monitor exit. These two rules actually say that I can move the operations into the synchronized block without breaking memory model. So this provides you with the simple thing to do log coarsening, for instance. You can also use this thing to move the operations over the volatiles without introducing new behaviors. The converse is not entirely true. So you cannot, for instance, move the write of X after the release because you're moving it out from the happens before. So now you will probably, if you do that blindly, you can probably introduce new behaviors which is not predicted by spec. If I have the very smart compiler who can say that nobody else, for instance, reads X in other places of programs, I could probably move that over the release. So there are special cases when you, for instance, do the volatile reads and writes in the constructor, and you by definition know that no operations are on this particular fields of this particular instance are visible to any other thread because the thread had not seen this particular instance. You can do this thing as well, but generally it is forbidden, and it's forbidden not by spec. It is forbidden by but by not having a smart implementation that could exploit other global information which could allow you to do this. The same symmetric things goes for read. You cannot really move that easily read before the acquire. But again, this is not something that is forbidden by the spec itself. It's just the implementations are scared to move these actions from acquire because that will probably introduce new behaviors. All right. So the people, I wanted to warn you that it's very easy to reason about reorderings and what implementations do or do not, but it is a dangerous line of thinking, because if implementations do not, for instance, do this kind of optimization of reordering, non-Roach model reordering, it doesn't mean they will not be able to do this in future. So code by spec, not by implementation. Let's go for a few simple, final simple examples. So what does it print? We have the variable a and we have a flag ready. And in first thread, we write 41, 42 and set the flag, and then write 42. And the second thread, we busy wait and ready and print a. So Oleg, what could this program print?
So it could really print 43. And the reasoning is that, well, we just execute the first thread, and then the second one somehow it flushes all the memory, so 43 propagates everywhere, and then we execute the second thread, and we read that 43. Or we can read 42 if the second thread just observes ready is being set to true, and then instantly observes the last write of A in the happens before order, which would be like 42.
Yes. So why can't you see 41?
That's a good question, because we cannot reorder writes in the thread 1. So, and if we observe the value true in the ready field, since it's we through the happens before relationship, we must observe the last write to A, which must be 42.
Yes. So actually, if you build the execution which somehow magically reads 41, that execution would not be sequentially consistent, because if you build the happens before order through ready, the write of 42 to A would be the intervening write, and you should see that intervening write, not the write before it. So yes, it prints either 42, which is the latest and happens before, or 43, which is erase. So what does this guy print? I just dropped volatile.
Oh, this should be able to read whatever. So no, it can. Oh yeah, maybe it can. No, it shouldn't. It shouldn't be able to read 41, I guess, but it can read 0. It can read 42, 43, because those were also valid outcomes in the stronger model with volatiles, and it can just not finish if we really optimize the second thread.
Yeah. Let's back up. Let's talk about why can't you see 41? 3 minutes ago, I told you that you can see 31 in the previous example because there is the intervening write of 42 in A. And in happens before consistency, you have to see that intervening write, not the writes before it. Right now, you don't have happens before. So right now, if you read something from A, you can observe any write that program made anywhere. So, and this thing is every answer is possible. You can read, well, not every answer from the list above. It can read 0, 41, 42, 43, or nothing. It is the unordered tree. You can see 41, 42, or 43.
Okay.
All right, I will pass the benchmarks because blah. Timing, because of the timing. Out of thin air values. So sequential consistency data race free seem to be saying that, well, all you need is log. You just say, look, if you have something shared between the threads, you should use synchronizations to order the access to them. You don't really care what happens within the thread if you're messing with the local data. So the optimizers are probably free under SC-DRF to do local code transformations unless you hit the synchronization primitive. Because if that local transformation somehow magically messed with the conflicting access which user had not synchronized, then user would have something that's coming for him. He is not covered by SC-DRF to begin with, so he had the erase operations at all to begin with. So it seems like a simple set of rules. My optimizers do local code transformations. They are allowed until I face the volatiles. Everything is fine. Even if I face volatiles or synchronized, I can play it with some simple set of rules like Roach model without doing global analysis. Turns out it's not entirely true. There are cases when local transformations break sequential consistency, and this is the nice example which I think is present in every single JMM paper. So we have global variables A and B, and one thread reads from A, checks it for 0, and if it's not 0, it sets the other variable as 42, and the other thread do the vice versa. So remarkably, even though these threads are doing actions on global variables, this program is correctly synchronized because all the sequential consistent executions have no races. In all the executions, writes to B or A never happen. So I just read things from A and B, check it, and terminate. So the only possible result that I get in R1 and R2 is 0, 0. Now, suppose by some wisdom, my compiler wants to do speculative optimization. It says, instead of checking for what's there in A, let's us unconditionally store to B and then conditionally roll back if something changed. So if you have this 3 lines of the original program, why don't we do something like that? Why don't we read something, read A to R1, unconditionally store 42 to B, check the opposite of the predicate, and if it happens to be true, then we will, reinstate the previous value in B. When you look at this contrived example, it doesn't make sense to do this, right? But it might be the result of some complicated optimization, which will in turn, provide this kind of reordering. So I will do, for the sake of example, I will also reorder the first 2 statements, and compiler could do that, or hardware can do that. It doesn't matter for me right now. And let me execute this with the second thread untouched. So now, if I execute this program, I store B 42 in B, switch to other thread, read 42 in R2. 42 does not equal 0. So I set 42 to A, switch back to the original thread, read 42 in R1. 42 does not equal 0, and I leave 42 in B. So this execution yields 42, 42. I made the speculation about the value of A. And under this particular execution, this speculation turns itself into this self-justifying prophecy. And this example seems very contrived, and you don't really know why you have to bother, until you realize that you can deal not with some, synthetic A, but maybe some special field which is called, say, system is security manager enabled. So if you allow these transformations in your language spec, you are basically deconstructing any security guarantee that your language provides. You can do the RACI update somewhere, and it can do this kind of thing. So what is out of thin air values? Notice that 42, if you look at the original program, there is no execution that could yield 42. And if you observe the result 4242, it looks like as if the program had pulled the value 42 out of thin air. So it's not there in the original program. Original program could not yield this result. In fact, I just pulled it out of thin air. GLS actually says that the out of thin air are forbidden. if I read some value that somebody else had written that for us before. And this is where it gets very, very, very tricky, because rigorously defining what is before is seems to imply that we have to have some notion of time, or global time, or global order in which all actions are executing, right? That again brings us to the strong memory model, and we don't want strong memory model. So we have to have some weaker guarantee. And there's the entire not chapter, but subchapter in JLS, which tries to give the weak enough and strong enough substance for that before thing. What does it mean to have before? The causality requirements. So that you cannot have the causality loops, which gives rise to the self-justifying optimizations. And this is how it's defined. And really, I tried to come up with a sensible way to to deconstruct this. But really, it is one of the simplest ways to explain how this works. So if you wonder how it works something like that. It works. You can assume it works. I will explain why you don't usually bother with this a bit later. So the commit semantics does these final checks for the executions to prevent causality violations. Neither of the checks before provides for the checks for the causality. This is needed to prevent causality loops in out of thin air values. So if I finally, if I want to see what executions can be used to reason about the outcomes of the particular program, only the executions which match all these rules are plausible, are the executions that I may use to justify the program behaviors. And this is why most of the time you don't really go into the commit semantics, because frequently you after you filter out the executions which are not interthread consistent, which are not synchronization order consistent, which are not happens before consistent, all the executions that you have on your hands are yielding the same outcome, and you don't really care which one of those executions is committable. One of them will be committable because one of them will, there is the existence theorem, which will provide you with at least one execution. In some corner cases, you have to do this, so you keep that in mind if you are really hardcore in JMap. And out of thin air values is really the forefront of memory model research, because nobody really knows how to rigorously specify this. The specification in JLS has some white spots which trip, formal verification and even the human reasoning on the large programs. So when C and C++ tried to come up with the same requirement, they actually wrote in the spec that out of thin air values are forbidden. But what does it mean for what is the out of thin air value is not very rigorously specified. So the working group for the C and C++ are, as far as I know, are trying now to give the formal definition of what is out of thin air value. And right now in Java, we have 3 ways to improve on this. We can continue as usual, but try to simplify or fix the formalisms that we have right now, so it would be digestible and verifiable. Or we can believe that our hunch is correct in that all these causality violations that we observed, like the example before, seem to be caused by speculative stores. So maybe preventing the stores to happen before, to happen out of order is enough to provide any causality violations, to forbid any causality violations. That will probably conservatively mean that there should be the memory barrier before each store, and that barrier is probably no up for the most hardware. Or you might just give up and ask implementations to be good. And that's not something that you would like for the language specification, because good is in the eye of the beholder, and you will have lots of trouble with verifying whether the implementation conforms to the spec or not. All right, finals. This is the final section of this talk. So what does this example print? You have class A, you have a field F, you have constructor which puts 42 to field F. And you have the global variable A, and one thread you do new A, and the other thread you read that A, check it for null, and print the F. What could this example print? Oleg?
Well, it could definitely print 42.
Yes.
That's good, and it can also print 0 because of the default value for F.
Mm-hmm.
And then it shouldn't be able to throw null pointer.
Well, let's first discuss why it can print null.
0.
Oh, sorry, 0. Yeah.
So it will print 0 if we initialize the new A, and we initialize A, but the value, the write to the F is not synchronized anyhow with the reading of that F.
Yes.
So we can observe the previously written value, which is 0.
Yeah, so the read of F is racy. We can read either the initializing store of F42 or the default value of F. So we can actually print nothing if A happens to be null. We can print 0 because it's the racy read. We can print 42 because we observed the value in from the constructor, or it can throw NPE. Surprisingly, because actually, as far as the JMM is concerned, the reads in the second threads are two independent reads. So even though the first racy read could bring you the non-null value, you can check for it, and then you go on dereferencing it, and you read it again. That second race could give you null. And you will experience the null pointer exception there. So how do you do that correctly? This is how. You do the single read, you null check it, you print it. But suppose I want to get only 42. What do I do?
You make the field final.
Yeah, I make the field final. And final, the rationale is that we want to have objects which are safe to publish via races, so that security would not depend on someone publishing the instances, always synchronized. So our, invariance, internal invariance in our objects would not be violated if our users misbehave, either maliciously or without the intent. Or, and this is not the target for finals, or we want to skip some of the excess synchronizations for the immutable objects. So, but the first motivation is security. We want to have some instance which is safe by construction, regardless how you abuse it. So, in this in this chapter, we will first look at the implementation, and we will say that the final field guarantees are actually easy to enforce. It's usually enough to order the final field initializations and the publishing of the instance. So it's usually enough to say for the implementation to enforce that all the initialization stores in constructors are visible before the store of the instance reference itself. There is also the second part on the reader side, that readers should not speculate about the field values until you observe the actual reference. The only architecture that could do that is alpha, and alpha is dead, so it doesn't concern us. But the formal spec is much more complicated than implementation. It is really hard to comprehend. And Vladimir Sitnikov, who is here on IRC, actually has the slides, the entire talk, which is devoted to untangling what is the semantics of final fields. So Vladimir, if you can do that, if you can put the link on IRC, that would be appreciated. So in spec, you say that there is a freeze action at the end of constructor. This is, I think, the only place in JML when you actually reference some high-level language element like constructor. That freeze action freezes the field values. And it freezes the values written in constructor in such a way that if a thread reads the reference to this new object with final fields, then it will always observe the frozen values. More formally, it will say something like this. It will say that if I want to figure out whether the write of the field is ordered with the read of the field, and the write of the field is here denoted by W small, and the read of the field is denoted by R2, you have to construct this particular chain of orders through the synchronization actions, through the action that publishes thread, through the action that reads the particular final field. The spec there introduces the two additional partial orders, that is the reference order and memory order. In that Vladimir's talk, there is they are introduced properly. We will not introduce it here because it's not essential right now. The idea there is similar to what happens before. If you only have the path from the write of the particular target field to the read of that field in another thread, which will pass the this chain of 5 actions, which includes freeze action, then you will have the happens before between the write of that field in constructor and read of that field in other thread. If you have another path that you can observe the other write of this target field with the particular read in other thread, then all bets are off. I will skip this part because it's better defined in Vladimir's talk. I will only provide you with the example which Jeremy Manson did in his article. So suppose we have the object T and we have the two global variables. We have the two global variables P and Q, and in first thread we initialize initialize the instance in T1, and we do the final field store 42, and we publish prematurely this object into P. Then we have the freeze action, and then we properly publish this object via Q. Then, in the simple example of the third thread, which only reads the instance from the global variable Q, if we try to reason, what can we read in R4? We can construct we need to construct the path to the write of F42. And we can only construct the path through the freeze action in the first thread. And that will force us to see only 42 in thread 3. In thread 2 is interesting because in R2, if I build the paths to the original write, I can actually build the another path that reads default value. I can bypass the freeze action. My happens before gets deconstructed. I don't have happens before that obliges me to see 42. So R2 can read either default value or 42. This is, if you look at closely at this, this is the premature publication. We prematurely publicated the object in P, in constructor, so that other thread saw that object under initialized, and it could see the default value. The example of T3 in the second thread, even though it treats the instance from Q, and you can probably build the proper chain through the freeze action in the first thread. Spec actually says that you can also have the path through P, which means that you can coalesce the loads of P and Q into one, and R3 could also be 0 or 42. So if threads saw the under-initialized object at least once, then all bets about finals are off. This is, by the way, the answer on the usual questions: how does reflection set the final fields without obliterating stuff? It doesn't publish the objects before setting the final fields there. It's too late to set final fields after you leaked the object. There's no guarantees about that. There are only guarantees if you haven't leaked the object yet. Again, Vladimir's talk talks about this with finer detail. So the pragmatics for finals, not only security, but also that the final fields are, cacheable. In the sense that the old references to the objects are created equal. You don't have to track whether the object that you are referencing right now is initialized completely or incompletely. As soon as you see the reference to the final field, you can cache it, you can use it, you can align it, you can do whatever the hell you want. If a user on the other side had leaked the object incorrectly to you, then he hadn't have the guarantees for the final fields to begin with. All right, as the parting example, what does this guy print? So the same class A, final field F, the store of 42 to F, the same example on the bottom. We initialize and store the object instance in the first thread, and we read the instance in the other thread and print the value of F. What could it print? Oleg?
So, well, we cannot observe the null pointer because we safely cache the A in the local variable. We definitely can observe 42 because that's just natural, and if we wouldn't, that would be crazy. We cannot observe 0 because we shouldn't be able to observe 0. So we can observe nothing because there is an if. So if the second thread runs through before the first thread actually initializes A, then we don't see anything. And we cannot observe 0 because
Why?
it's well, because we cannot see under initialized object because we don't leak. Or maybe it depends if we leak the instance from the constructor of A.
So the spec says that you have to have a freeze action at the end of constructor. There is no constructor here, right?
Yep.
Well, actually, no. There is a constructor. What you see here is the instance initializer, which will be the part of constructor. So that store of 42 to F is actually the part of constructor. So it has the same guarantees as just initializing in constructor. In the same way, if we just inline the assignment just in the field declaration, it will be the same. It will also be the part of constructor.
Okay, then we cannot observe 0 because we publish A safely.
Yeah. So if you want to trip someone rigorously, following the spec, showing this example, it doesn't match one-to-one to the definition of final fields with constructors, but you have to also look elsewhere to match it. All right. So in current spec, final is somewhat harsh. So what if a field is initialized in constructor and never ever modified? Like user just omitted final for whatever reason, just forgot it. Should we inflict pain in this scenario for the user or not? Or should we play nice and say, well, okay, if it's not effectively final, if it looks like final, maybe it should have the same memory semantics. But this is the this is a didactic question, right? It's the question about what do you want from your users. There are corner cases where you can't really, when you want the semantics of finals, but you cannot have them. So for instance, if you have an atomic integer, which already has the volatile modifier for its value, an atomic integer has the constructor which accepts the initial value. So you would like to see that if my user constructed the atomic integer with some non-zero value, passed it via the race, that all the readers of this atomic integer will see that initial value. Volatile itself does not provide you that guarantee. Only final provides you that guarantee. But you cannot put both final and volatile at the same variable. It is the violation of spec. So the question for GMM9 is actually whether we should extend the same guarantees to the old fields and all constructors, regardless of whether a user put final on the fields or not. There are some benchmarks which say that the cost is minimal. I can talk about that if people stay around. So I will quickly go through the conclusion, and then we can rewind to any other section there. I understand that when people are exposed to this, they get their heads explode, because really the rules are really, really complicated. So when we were discussing a particular nasty corner case in GMM, this quote was born: that the best way to build up, the best way to deal with concurrency is to build up a small repertoire of constructions that you know the answers for, and then never ever think about GMM rules again unless you're forced to do so, because literally nobody likes figuring things out from the GMM rules as stated, or can even routinely do so correctly. This is one of the reasons we need to overhaul GMM someday. And it's particularly interesting that this quote is actually from Doug Lee himself. So even Doug understands that you're not using GMM as stated. You're just using it once or twice to build up the recipes, prove those recipes works, understand in what conditions those recipes works from the GMM as stated, and then just reuse those recipes over and over again. So there are known problems. Known problems is that there is also the GSR 166 cookbook, which is called Gel Memory Model for Compiler Writers, which explains the conservative implementation of memory model, of what minimal steps the implementation should take to be GMM conforming. There are some problems with cookbook because humanity has discovered a few nasty corner cases in non-trivial architectures which cookbook does not address. Some library primitives are not expressible in the current model. For instance, lazy set, which is not a plain write, but also not a volatile write, and has weird ordering constraints which are not expressible in current GMM. GMM is also specified for Java. Other languages which target JVMs are not covered implicitly by this spec. So there is no spec on the bytecode level, for instance. Most languages, I don't know what they are doing. I think they are just piggybacking on what's provided for Java. And the formal spec has some issues, especially in the out of thin air values causality requirements, things that require rehashing. So this is why we have Java memory model update, and everything that I told about under GMM9 is the part of that effort. You can probably read more there. So if you want to read more, this is the list of books: Java Concurrency in Practice, The Art of Multiprocessor Programming, which is very algorithm-centric. Sarita Advi has Shared Memory Model, a tutorial, which is more hardware-oriented. Paul McKinney has the very nice book, which is called Is Parallel Programming Hard? Duh. And if so, what can you do about it? Very nice thing. And if you want the formal dive-in into the Java memory model, you might want to read Manson's Java memory model, or some other interpretation. It's actually the interesting thing. There is the formal spec, and there are lots of academic papers trying to make sense of that formal spec, just as we did in this talk. So if you don't understand how the memory model works, you can read around and then see how other people try to gain the understanding what the memory model really means. And I think that's it for the talk. I have a few examples for atomicity breakage, for unsafe publication, unsafe constructions, and I have benchmarks which I can also show. So shoot, what do you want to do? I have enough time on my plate to continue. I realized we had overrun, but that was, I think, planned. So, Simon, Oleg?
So first of all, thanks for the awesome session. I enjoyed this personally a lot. I think we can dive into IRC to see if there were some questions. Since you were asking me about all those examples, it felt really like I should totally focus on following the session, and it wasn't that easy. So it will take a minute for me to parse through IRC.
All right, so there is a good question about the benign data races, and I think Stuart had already explained a lot about that. So there are a particular, the common wisdom is the races are bad, because if you have the races in your program, you are getting out from the sweet cradle of sequential consistency data race free guarantees. But there are cases, as Stuart says, when regardless of how the race is getting resolved, you will always have the same result. I think the canonical example is the string hash code, which actually updates the hash code field under the race without synchronization. But because the computation of this hash code is idempotent, regardless of what you had read under the race, if you had read the uninitialized hash code, you will recompute exactly the same hash code the second time around, or the third time around, or every single time you will compute it. So there are some edgy things that you can use. One of these edgy things is benign data race. But unless you are comfortable with reasoning with Java memory model and understanding, how to reason about the outcomes of the program, it's really dangerous to go that route. All right, I see Vladimir has the link to his slides. Thanks. Yes, yeah, only the final fields are frozen. And regarding auto-thin-air values, GNOME allows reads to see writes that occurs later in synchronization order. This aligned with load store. Yes. The details about this speculative stores is really complicated. I think the part of that is about speculating over control flow. So the example that we see in the slides, for instance, is speculating over control flow, and probably the load store is providing the breaks speculations over the control flow, among other things. But again, I don't think anyone on this planet has the answer for this question right now. I know a lot of people who are trying to answer it, but no luck yet. And that, I think, everything.
Yeah, I have maybe a more philosophical question.
Yes.
So through this session we went and we defined the requirements that we want JMM to impose on the implementation, and it wasn't easy. So reasoning about those things are not easy as well. And you said yourself that maybe just building a repertoire of small snippet that you know how to work, how they work is the best. So do you think it's actually that required to think about Java memory model when you develop an arbitrary average application, or maybe it's just better to drop synchronized, make everything synchronized, and make everything volatile, and then leave it to specific, very smart people to remove those things?
I think that will never happen. I mean, you cannot force people to synchronize everything because they will cry performance or something like that. I would certainly like to see, I think this is the route that most programs follow. They first make it right, then make it fast. So you do all the synchronizations that you can possibly do, and then you relax the synchronizations in the particular places when you need the highest performance. Now, the first part is easy. That's no-brainer. The second part is hard because then you actually have to understand what can you relax and where you are crossing from the sweet cradle of JMM into the shadow zone when implementation do something, but today maybe they will do something else tomorrow, and you can't really predict that. Or maybe this particular thing only works on one particular architecture. And I mean, I actually said that explicitly, that in your day-to-day work, you are not required to know JMM at this level. It would be insane to waste time on reasoning about the programs at this level. But you have to know where to go if you want to prove whether the particular chunk of code, the particular recipe that you're using, is correct, and whether all the preconditions that you have there actually match the preconditions for correctness of this particular recipe or not. This is where you have to learn JMM. Actually, the worst case scenario that I see in the industry is that a handful of people know how to interpret JMM, and everything else is folklore, which is almost always wrong. And you have lots of broken programs because people just blindly believe something and don't have the instrument and the techniques to derive the actual correctness proofs. What we had done here is the introduction into this low-level spec that you can use to reason about the particular recipes or particular recipe's correctness. I think that's an essential skill for the senior and above guys. They will have to employ this a few times in their programming lives, or maybe they will have to employ this regularly if they are really, really into high-end concurrency.
But then again, do you have any suggestion about maybe there are tools that can help us, maybe not to formally reason about stuff, but at least?
Yeah. So the problem is the problem with testing. You can test that something breaks. You cannot test that something doesn't break always, right? So JC stress, for instance, is something that we are using to try to break implementations on concurrency front. But again, we can, it doesn't prove that something works correctly. It can only observe that something breaks. I actually have the examples which I can show with this tool, and we can do this after the Q&A session for the interested folks. I do know the NASA has the tool which tries to construct all the possible executions for the programs and see what are the outcomes that derive from that, that can be derived from that program. But since you're facing the combinatorial explosion of all the possible executions as your program grows, so it usually works on the small programs. I do know people who are building tools to figure out what is the actual hardware memory models, which are also, the funny thing is, Java started and completed even the second overhaul of Java memory model when the hardware memory model was very loosely understood. This is why, for instance, Cookbook has some white spots. Intel, I think, had specified at least some part of hardware memory model in, not so long ago, like 10 years ago. It wasn't there before. So academics actually spent considerable time building tools and building test cases to figure out how hardware behaves. Other than that, I'm not sure. I think there are plenty of tools that try to do all sorts of interleavings, like say now we have this unit test and we say that here thread sleeps for a cycle or two, and try to break the concurrent implementations in that way.
Cool. So I think almost 3 hours of JSM is pretty much going to melt most people's brains. So I think we'll bring this to a close around now. I just want to say absolutely massive thank you to Alexei from the virtual Jargon and all its members. It's always great to get real deep technical superstars around the community onto the virtual Jargon. We certainly got that today with a real masterclass on JMM. I'd like an interview, I believe, tomorrow or very soon this week. So it would be great to maybe get some of those exercises that you were talking about, and maybe the benchmarks on something like that we can do offline and make that available to the group as well. So maybe we could do something like that. But yeah, I just want to say massive thank you. And I guess, Alexei, if you wanted to stay in IRC, if anyone had any more questions.
Yeah, I can actually stand and hang out and show JC's threads if you want.
I've actually got to run, so I can't, and I have to stop the broadcast here. So I can't do that now. But we can do that perhaps around the interview time when we next do that, and we can make that available to the whole group as well.
All right.
But yeah, massive thank you to Alexei, and thank you to everyone else in the in IRC and Stuart as well for joining us again in IRC. Big thank you to Oleg, as I was away a lot of the time on this session for continuing this optimizer for Eclipse release, so I was pulled away. But thank you very much to Oleg for saving my bacon and answering some of those questions. Cheers.
I enjoyed this a lot. Thank you, Alexei. It felt like a private lesson that the whole world can watch. So I enjoyed this.
Yeah, I hope it wasn't that. I hope it was understandable. If you don't understand something, it's not because you're dumb. It's because the topic is really difficult. So if you want to understand something, and if you want to rerun some part of the slides, you can wait for Simon and Oleg to post the video, or you can use the transcript that I already did for this talk and reread specific parts.
Yes.
So
this video would be
people on the planet that I know are getting JMM after the 5th or 6th reading. it's totally expected that you will not get it for the first time. So.
And we'll absolutely push this replay across all our lists. And Alexei, I believe you're a host on the Meetup site for this event. So your questions, you're welcome to add a comment to that Meetup event, and I believe Alexei will get notified that with an email. Or alternatively, your Twitter handle is @Shiplev, is that right?
Yes, right.
Okay, awesome. So I'll make that available as well. So thank you everyone for turning up. Our next session is on the 18th of March, which is a week today, and that's on OSGI and how you would use modularization in the cloud. And that's with Bert Ertman from the Netherlands, who used to run the Netherlands job for just over 10 years. So we've got another great speaker for you next week. And I'll provide some more information, as I mentioned midway through the session, on what the book club entails, how you can join that, and what our next steps are. So thanks very much, guys, and thank you everyone for joining. See you soon.
Yep. See you. Thank you.
Bye-bye.